Hello everyone, welcome to the next episode. Uh, this I want to talk about the soldering iron power. That's the actual power that heats up the element inside the um, soldering tip. We have this MOSFET and transistor setup, and I want to explain why we're using this setup and not just a MOSFET. So what I'll do is, let's just take this out of here and just put it into a circuit, which is this basically. So what we've got here, we've got pulse width modulation coming in to this transistor, which turns this on and off, and in doing so turns this MOSFET on and off, and we're using a P-channel MOSFET. The question is, why do we need to use a P-channel MOSFET on the positive side of the power? We could just use something like this, put a big X through here, but because this is why we can't use an N-channel MOSFET. This does exactly the same thing. We have a pulse width modulation coming through here, which turns this MOSFET on and off, and that will turn the power off to the heater element on and off. Simple. Fewer components. We don't need in the other circuit we've got this diode here. We don't need that. We've got that inside our MOSFET here. So the reason why we can't use this circuit is because we're actually turning off the negative supply to the soldering tip, and we actually need to turn off the positive side. So we have to use a P-type MOSFET, but we have to have that controlled by an NPN transistor, because our pulse width modulation works on the positive side. In the on state, we need, this is our pulse width modulation. We want this circuit on when we supply a positive supply here. So basically our pulse width modulation comes out like this. At 50%, half the time it's turned on, and then half the time it's turned off. And half of the time it's turned on, half the time it's turned off. And this equates to half the voltage that we're actually supplying on this rail here. If we're doing 80%, then it stays on for 80% of the time, then off for 20% of the time, and so on. And if we're doing 100%, basically we're just switching it on permanently. And going the other way, we can have 20% by having it on only 20% of the time and off 80% of the time. Or we can have it off altogether, and basically we're just switching it off. So this is the signal we're putting in, so this is controlled by a positive supply. So we need this transistor to actually turn the negative, sorry, no, it's not the negative. We need this positive, this transistor, so we can control the P-type channel MOSFET, which is actually on the positive side. And we need this diode here because our transistor doesn't have a parasitic diode inside. Because we're now going through a transistor and a MOSFET, we need to put a diode in there to stop our spikes coming back, because essentially we have a coil here, just like in a motor and anything else. When we have a coil, we turn it on and off, you'll get a spike coming back in the opposite direction. So we need this diode here to stop that frying this transistor here. And so why do we need the positive channel MOSFET? And to just go in one moment. Yes, sorry about that. Right, so why do we need to control the positive side? Well, that's because, I'll just bring the circuit back. here is because we have this circuit where which I went through before, and we're actually at times we want to take a measurement from our thermocouple, and for us to take a measurement from our thermocouple we actually need the positive side turned off, and that's why we actually use this a P-type MOSFET. Yeah, we're on a P-type. This is why we use a P-type MOSFET to turn the positive side of that. If we were to use an N-type MOSFET and just turn the negative side off, this would still be giving our voltage to this rail here, and this is what we need to turn off. I explained this circuit earlier. We need this rail below the forward voltage of this diode. So to get that, we actually have to turn the positive rail off of our supply to the heater element. So that is the reason for this type of circuit here. So I hope that made sense, basically. So we've got this here, which is doing the job of this, but it's actually protecting this one here. And so yeah, that's why we can't just use this simpler circuit and just control it on the negative rail. And I hope to be able to show you this. So what I've done is I've set up my little tiny well, yeah, with T88 to actually show you the pulse width modulation and how it works. And I will go through the code. In basically what I've done here, I've set up a little potentiometer here. This will go from VCC to ground, so depending where I wind this up, it's either this voltage or it's no voltage down at the ground. So it's somewhere in between, depending where we sort of wind the potentiometer. And that basically what I'm doing is here is doing a temperature emulation. I needed this D9, so I couldn't set up my 7-segment display because I could, with this T88 I can only get pulse width modulation out of D9 and D10, so I've had to use this pin, so I've given up. And I also fried well, I'll explain it later as well, but basically the only op amp I had of the right value is no longer working. Anyways, so I'm just doing like an emulation, whereas this here is so I can manually change the emulated temperature. So what this pin is doing is getting in a proper circuit. This pin here will be getting the voltage from the K-type thermocouple, and it would convert it using the analog to digital converter into a figure. The microcontroller will do some calculations, and then it will all output a pulse width modulation. So I am not controlling this pulse width modulation here. All I'm going to do is control the input. So I've put a potentiometer here so that I can emulate the signal, the voltage, analog voltage from the op amp that goes into this pin, and then I can actually physically change it without having to warm things up and cool things down. We can take a look at what the PID is doing to control the pulse width modulation to heat up the element and to emulate the element getting heated up. I've put an LED so it should get brighter when the pulse width modulation is high. That means well when the period is greater than well, sort of like in the 80%, and then it should go dim when period is sort of about 20%. So this is emulating our heater visually, basically. So you can, the more it glows, the more heat we're putting into the heater, if you get my meaning. So I've just made this circuit so I can control it manually, basically. It's basically doing an emulation of the circuit that we have here, basically. We have pulse width modulation coming in. This is turning this MOSFET on and off, and that heats up the heated element here. And like I say, we need it on the positive line because we actually need to turn the positive line on off to take a reading from the thermocouple. Yeah, I think that's about it. So what I'm going to do is I'm going to set up my camera on the solderless breadboard with this circuit on, and I'm also going to put my oscilloscope on as well, so we can actually see the pulse width modulation altering as we alter the emulated temperature. So just one moment. Here we go. This is my solderless breadboard again, and I've just stuck my little tiny here, and I've got this potentiometer just wired up to the board there, and from the board I've got my LED and I've got my oscilloscope attached to the same wire going to the LED. So basically what I will do is emulate the temperature going up and down by turning this potentiometer. So it'll probably be off screen, but basically what I'll do is I'll just say I'm turning it up, turning it down, and you'll be able to see the pulse width modulation. So I'll just bring my oscilloscope in. Oh, before I do that, I just want to mention how I managed to fry this. Right, remember that these two diodes here, basically, these are the protection diodes. But and if you ever do something like this, basically when you add a high voltage, so this actually runs at 5 volts, and I want you to stick sort of 12 volts in here, or 20 odd volts into my soldering iron. These two diodes were supposed to be protecting it, but if you know about solderless breadboards, the connections aren't that they aren't that good. If you happen to just knock one sort of like that, it might break a connection, and basically that's what I did. I sort of knocked me. I should have hard soldered these together to protect this, and because I didn't, they were just stuck in my breadboard, and you just tap one of these, it loses connection, so it's no longer holding the high voltage to ground, and it let it straight into the breadboard. So yeah, when you've got a circuit like that, I think in hindsight it's best to hard solder them so that they will not lose contact. Anyways, it's a learning curve. Right, so I'll bring in my oscilloscope, and you can see there we've got a pulse width modulation. What we can do is we can zoom in. So if I zoom in, you can see that it's only on for a fraction of the pulse. I'll just zoom out again. So you can see one. So we can see the length of the pulse, and you can see it's on for. Have I got period? Oh, yeah, there's period. Yeah, I've got it turned on. Duty 0.3. It's 0.39%. Actually, I wonder, should I just pull that out? No, I'll leave it as it is. It looks alright. The thing is with this, what I can do is I can how can I do that? I'm sure I could do. Oh, did double click? I'm sure I could drag this out actually, but I don't know. I did it the other time. Oh, is it zoom? Oh yeah, there we go. I can zoom in. I can move this bit out of the way now. I'll control this on my other monitor. And so now you can hopefully you can read that now. I'll just make it a little bit bigger, like that. So now you can actually, can you see that the duty is 0.39%? And all we need to do is to see this this bulb light up. So it's pretty dim at the moment because we're only doing this percentage. But if I was to turn the temperature, it thinks the temperature is okay at the moment, so it's giving a very little current. But if I was to move my potentiometer down to say that the temperature has dropped, to emulate that the temperature has dropped, then the pulse width modulation should alter. Well, oh, right. Now I've got PID working on this, so because it's been sat like that for so long, it may take a while for it to actually do anything. So what I'm going to do is, once I find center, it's going to be about there somewhere. I'm just going to reset the microcontroller. It could be that I just need to tap some frigging wires, because I might not be getting oh, there we go. Right, so if I say the temperature is going down, then you can see, I'll turn the potentiometer, you can see that the pulse width modulation will turn up and add more current. And then when we get up to temperature, and so I turn the potentiometer so to say that the temperature, we're now up to temperature, you can see that it puts less current with the pulse width modulation. And then as the temperature goes down, it increases the amount of current to the LED, and as the temperature goes up, it reduces the amount of current. So all I'm doing here is manually turning the potentiometer to tell it that the temperature is going up and the temperature is going down, and the PID actually takes some calculations and works out how to keep it steady at a standard. I'll go into more details actually when I come to the code and show you what's going on through the code basically. But I just wanted to show you that it actually, by altering the input, the output is altered by the PID. And I'll explain PID a bit later on when I come to the code, because I've got notes there and it's going to help me remember. So anyway, yeah, so basically this is what's happening when it's heating up a soldering tip. The pulse width modulation, it keeps changing, which is controlled by the PID, which looks at the temperature and alters the pulse width modulation to suit, so it keeps it at the correct temperature. So I hope that was of a bit of interest there, so you can actually see it actually doing its work as it works it out. I'm just going to pause it there, and I'm going to bring up the code. Here we go, here's the code part. Like I said, this bit isn't a long video, hopefully. I'm sure many know what PID is. I've written here because it's proportional integral derivatives. This means it does two calculations in theory, really. Well, it does a quick calculation and an overall calculation. It sort of does quickly changes a state and then a value, and it keeps track of the values it keeps using and gives sort of like an average of that value when it changes things, so it gets more accurate. The more times it calculates something, the more accurate it gets at changing things. I've done. Oh, let me just zoom in again here for you. Or did I do that already? Is that? I think that's. I hope that's big enough for you to read. Hang on, let's just make it bigger. Yeah, there, it's all there. So this code here is going to read a value set by potentiometer. That's me messing around, emulating the temperature reading, saying whether the temperature's gone high or gone low. Then it's going to adjust the pulse width modulation to emulate the heating of an element, and that's derived by using proportional integral derivative to set the temperature of the soldering iron, so it keeps it at the temperature you've told it to do. I've written it. I've written it here because it's a lot easier to read than it is for me to pause it, read it, and I'll just scroll up a bit more. And I've done a summary at the bottom here. So basically there's 3 settings that you need to do. One is like a quick setting, one is like an overall setting, and one just to keep things balanced basically. So you start with the KP first, and just make sure that it starts actually working. So you set this value so that you can actually see it turning on and turning off and turning on and turning off, and just make sure it's altering the value all the time, and then you do the next one to sort of like just make it not do its in like massive steps. Basically it sort of does a bit of thinking and remembering, and if you get a lot of oscillations and it's tending to overshoot too much its adjustment, then start tuning with this value basically. So yeah, so I've just set my pin that I want the pulse width modulation out, which was this one here, my D9. So my D9 is set, and my sensor pin, which I want to take a reading from the analog pin from the potentiometer, which I have done. Oops, wrong button. Here, so this is A6, which is here, A6. Also what I've done is before that in my notes there, yeah, this is I've written this in the Arduino architecture to a point where, but the actual pulse width modulation, I've actually written the code in the AVR architecture. Yeah, we'll come to that. So these are all my variables. I've got my circular buffer. I went through that before, because we're going to take readings from this variable resistor. It may get sort of, you just wobble it a little bit and it'll give sort of readings, and you get spikes and stuff. So you want to take an average of say 10 readings at each time, and I think I explained that circular buffer before. And then we've got our PID constants here, which is our KP. These are the ones that you adjust. So well, these 3 values, these are the ones that are adjusted to set up the PID. Basically, that's what I'm talking about here. The P, I, and D of the PID is these 3 here. So that's them values. These could be anything. These are just set as basic starting points. This set point, this is for the emulation. This would be set. So imagine that you had a soldering station and you set a temperature. That's what this number is. This is what you've set the temperature to, and this is what the PID is going to try and achieve all the time. So yeah, this is just because this is an emulation of the actual code. I've just put a fixed value in there for now, but that would be set on you would set this value on your machine. The user would say, I want 127 degrees, say, and that's what that is basically. Well, I've written it there, the desired temperature. So yeah, and then we've got some variables. So it needs some variables that the PID can actually use to keep track of what it's trying to achieve here and get there. So these just store variables that keep changing throughout the use of the program. And this is just timing. So I don't want to check all the time, constantly. Basically, we just check every 100 milliseconds what the temperature is, and then we work out the pulse width modulation every 100 milliseconds. You can change this, make it longer, shorter, whatever. This is my average temperature. Actually, that should have gone up there. There we go. That's just, I like things tidy. Sorry, I just like things to look like that. Yeah, so we set our pin mode, which is output for the pulse width modulation. That's so our pulse width modulation pin wants to set into output, and this is where it's no longer Arduino code. This is AVI code. This is where I'm actually using the actual definitions in the AVI side of things, and what we're doing is we're setting the pulse width modulation on our timer 1, but in non-inverting mode. So basically our timer goes tick tock, tick tock, tick tock, tick tock, and then this is our duty cycle. So basically what this does, whatever value we set here, we change this all the time. We're actually changed. This is what we change in the PID. This gets changed constantly, and what this value does gives us our basically gives us out this bit here. It's the period, the time that it's on for. So if this was like say 50%, the value is actually between well, we'll see. I think it's 0 and 256. Yeah, PID output. So we keep it within it's in a range between 0 and 255. So that's mapped to sort of like 0 to 100% sort of thing. So basically, what I'm showing here, if it was in here like 50%, so this would be this to get this value we were doing maybe 126, 127, which is half of 255 basically, I think. So yeah, so basically that does our duty cycle, and then this is what actually alters the duty cycle. And then we've got our pin sensor, which is an input, so we need to get an input for our sensor pin, and this is just setting our buffer, our circular buffer, to all zeros to start with, because we've got it all turned off. And then this is our main loop. So basically in our main loop we update our buffer, we read the analog pin, get on sensor pin, get a value, and we stick that into the buffer. So rather than write all the code there, I've just done this little function basically that puts the buffer into the next segment of the buffer, the circular buffer, gets rid of the last one, and so on, and it goes round and round in a circle. So that just keeps the buffer updated with the latest reading from the analog pin. So then what we do is, to get the average temperature, we just divide the buffer, the sum of the buffer, that's all 10 readings, divide it by buffer size 10, and then this is here to actually compute the PID, and we do this every, so like I've said previously, we do that every 100 milliseconds. So if 100 milliseconds, this line, if 100 milliseconds has elapsed, then we then do the compute the PID, and that's it really. That's all we do. And so the PID is this bit of mathematics. You can look at it and you can see what's going on. I've put some notes in there, and then we just make sure that it's within 0 to 255, and then we just alter the period, the duty cycle, by the output that we've just calculated here. That's the actual calculation. So yeah, it was pretty simple. So yeah, I just, this hopefully was not a long video. I just wanted to explain this circuit really, and the reason why that we are controlling it on the positive side of the current, on the positive side, and not just on the negative side. We could have, you know, if we were just lighting a light bulb, we could have just used something simple like this, but because we want this actually turned off on the positive side, we have to use this setup to actually turn it off, so we can actually get a reading using this circuit here. So we can use this circuit when this is actually turned off. I hope this makes sense with the previous video that I did. I don't think I actually really explained it well, but I hope you've managed to pluck something out of this and got an idea of what we're doing. I think this is about it really for the preparation for Project X. Oh, one thing I do want to say is that when we do, if we make our own, I won't be using an op-amp. What I'm going to be using is one of those, what was it, MAX, I've forgotten now, let me just look it up, MAX 6675. I think it'd be better using one of them than trying to cheap out with an op-amp. So yeah, I hope you find this a bit interesting. Well, I'm rambling. Catch you later, guys.